dear students, in this video we will study about the gases, the measurement of mass, volume, pressure and temperature of the gas laws and the postulates of kinetic molecular theory of gases. So let's begin. So as we know that matter exists in three different states, that is solids, liquids and gases. Have you ever thought as why different elements or substances they exist in different states under normal conditions of temperature and pressure? For example, bromine exists as liquid, iron exists as solid and oxygen exists as a gas under normal conditions of temperature and pressure. The simple answer to this question is the competition between the ordering effect of the molecular interaction energy and the disordering effect of the thermal energy. Molecular interaction energy keeps the molecules together while the thermal energy moves them apart. This competition determines whether a given substance under given conditions is a gas, liquid or a solid. Thus, the existence of the different states of the matter is nothing but a balance between its intermolecular interaction and the thermal interaction between the particles. The occurrence of intermolecular forces is the least in gases and most in the solids, whereas the occurrence of the thermal energy is the least in solids and the most in gases. There are only 11 elements in the periodic table which exist in the gaseous state and under normal conditions of temperature and pressure, and these are hydrogen, helium, nitrogen, oxygen, fluorine, chlorine, neon, argon, krypton, xenon and radon. So now we know that the amount, pressure, volume and temperature are four most important measurable properties of gases. Now these we will describe here one by one. So first of all, measurement of the mass. The mass of a gas can be determined by weighing the container containing the gas and then emptying the container by taking out the gas and weighing the empty container again. The difference between the two masses gives the mass of the gas, and the amount of the gas is usually expressed in terms of number of moles, which can be obtained by dividing the mass of the gas by its molar mass. So this is the equation, and the mole can be converted into the number of molecules by using the relationship this 1 mole is equal to 6.022 into 10 raised to power 23 molecules. Now we will see how to measure the volume of the gas. Now a gas fills the whole of the vessel, that we know. Hence the volume of the gas is equal to the volume of the container. The SI unit of the volume is meter cube, and the units commonly employed are centimeter cube or decimeter cube. However, the units like milliliter and liters are also used. So these units are interrelated as, now 1 meter cube is equal to 10 raised to power 3 decimeter cube or is equal to 10 raised to power 6 centimeter cube. 1 milliliter is nothing else but is equal to 1 centimeter cube, and 1 liter is nothing else but is 10 raised to power 3 centimeter cube. So these units are interrelated with each other. Now we will do the measurement of the pressure of a gas. The instrument used to measure the atmospheric pressure is called the barometer. This is the barometer. It consists of an inverted tube filled with mercury in a dish of mercury. The height of the mercury column above the level of mercury in the dish is a measure of the atmospheric pressure at that place. As pressure is force per unit area, the pressure obtained in terms of height of the mercury column is given by this relationship. Pressure is force by area is equal to H rho G, where H is the height of the mercury column in centimeter, A is the area of cross section of the tube in centimeter square, rho is the density of the mercury at room temperature in grams per centimeter cube, and G is the acceleration due to gravity. Now a standard or normal atmospheric pressure is defined as the pressure exerted by a mercury column of exactly 76 centimeter at 0 degree centigrade. This is the pressure exerted by the atmosphere at the sea level. The smaller unit commonly employed in expressing the pressure of the gas is millimeter or torr, and therefore we can say that 1 atmosphere is equal to 76 centimeter of the mercury level, or is equal to 760 millimeter or 760 torr. And unit of pressure commonly used nowadays is also called as bar, and these bar and atmosphere are related by 1 atmosphere is equal to 1.01325 bar, or 1 bar is equal to 0.986923 atmosphere. The SI unit of pressure is pascals also, and 1 pascal is nothing else but 1 Newton per meter square, or equal to 1 kilogram m-1 s-2. So all these units are very important and are interrelated with each other. So now this is the measurement of the pressure of the gas. Now we will do the measurement of the temperature of the gas. Now temperature is a measure of the extent of the hotness or coldness of the body. There are 3 different scales on which the temperature are measured. These are centigrade scale or Celsius scale, Fahrenheit scale, and the Kelvin scale. Kelvin scale is named after the Lord Kelvin, and from where this Kelvin scale came is when we start to cool a gas, then it was impossible to cool a gas below minus 273.15 degree centigrade, as after that the gas ceases to exist. Then this is the lowest temperature that can be obtained, this minus 273.15 degree centigrade. This was named as 0 Kelvin by the Kelvin on the Kelvin scale. So from here we can say that 0 Kelvin is equal to minus 273.15 degree centigrade, and Kelvin is equal to degree centigrade plus 273.15 Kelvin. So from this the Kelvin scale emerged. Now after this we'll do the gas laws. Now in this gas laws, as we know that now we have done the measurable properties of the gases. These are nothing else but are the temperature, pressure, volume, and the pressure of the gas. These are interrelated with each other, and this interrelation gave some gas laws. So in the gas laws, first law is the Boyle's law. What Boyle's law says: for constant temperature, the volume V of a given mass of a gas is inversely proportional to its pressure. So V is inversely proportional to pressure, and this equation will become V is equal to K 1 by P, or PV is equal to K, where this K is the proportionality constant, and this interrelation of V and P is shown in this diagram also. So this is the first law, and this is also called as the Boyle's law. Now the second law is the Charles law. What Charles law says: that at constant pressure, for every 1 degree centigrade rise or fall in temperature, volume of the gas increases or decreases by the ratio of 1 by 273 of its volume at 0 degree centigrade. And mathematically the Charles law is given by this equation, that is Vt is equal to V0 1 plus T by 273, where Vt is the volume of the gas at T degree centigrade and V0 is its volume at 0 degree centigrade. So what this says is shown in this graph also. So this is the Charles law, and the next law is the Gay-Lussac's law. And what this law states: that at constant volume, for every 1 degree centigrade rise or fall in temperature, the pressure of a given mass of a gas increases or decreases by the ratio of 1 by 273 of its pressure at 0 degree centigrade. So this is the mathematical equation of the Gay-Lussac's law, where Pt is and P0 are the pressures at T degree centigrade and the 0 degree centigrade. And this is the graph of the Gay-Lussac's law between pressure and temperature, keeping the volume constant. And the next law is the Avogadro's law. What Avogadro's law states: it states that all gases having equal volumes under the same conditions of temperature and pressure contain equal number of molecules, and 1 mole of a gas contains Avogadro number of molecules. These are nothing else but is 6.022 into 10 raised to the power 23. This means that 1 mole of each gas at the same temperature and pressure should have the same volume. So this is the Avogadro's law. Now the next law is the Dalton's law of partial pressure. What this law says, that if in an enclosed vessel two or more gases which do not react chemically are present, then the total pressure exerted by the gaseous mixture is equal to the sum of all the partial pressures that each gas would exert when present alone in the same vessel at the same temperature. So this is total pressure P is equal to P1 partial pressures of all other gases which are present in the same container. So this is shown here also, that suppose in this container we have the mixture of all these gases and these are the partial pressure of each gas, then the total pressure of the mixture of the gases will become the sum of the pressures of the gases which are in that particular container. So this is the Dalton's law of partial pressure. Now the next will be the ideal gas equation. Now we have seen the Boyle's law, Charles' law and Avogadro's law. Now combining all these laws will have that we know that volume is proportional to 1 by P, volume is proportional to T, volume is proportional to N. Now combining these equations, what we will have, V is proportional to NT by P and this will become PV is equal to nRT. This is the ideal gas equation, which is very important for the to study the gases. PV is equal to nRT, P is the pressure, V is the volume, N is the number of moles, R is the gas constant and T is the temperature. This gas constant has emerged from here. This is the proportionality constant and this R has many values which are very important to learn for the numerical problems also. We need this. So R can be explained as 0.08206 liter atmosphere per Kelvin per mole, or is equal to 0.08314 liter bar per Kelvin per mole, or is equal to 8.314 joules per Kelvin per mole, or is equal to 1.987 calories per Kelvin per mole. So this is the ideal gas equation. Now we will study the kinetic molecular theory of gases. Now the amount, pressure, volume and temperature are four most important measurable properties of the gases. These four interdependent variables describe the state of any gas. The interdependence of these variables lead to formulation of different gas laws such as Boyle's law, Charles' law, Avogadro's law. At the time of their enunciation, the various gas laws were only empirical generalizations based on experimental observation. There was no theoretical background to justify them. In the 19th century, however, Cronin, Clausius, Maxwell and Boltzmann developed a theory known as kinetic molecular theory of gases, which provided sound theoretical basis for the various gas laws which we have studied just now. So the main postulates of the kinetic molecular theory of gases are shown here, and now we will study these. So what are the postulates of kinetic molecular theory? First is that all gases consist of very large number of minute particles called molecules that are in constant rapid motion. So that is clear to us. Now the second one is that the gas molecules are perfectly round, very hard and separated by large distances. Their actual volume is thus negligible as compared to the total volume of the gas, because the gas molecules are far apart from each other. They have large volume and that's why their own volume is very negligible as compared to the total volume of the gas. Now the third postulate is the gas molecules are in a state of continuous rapid motion in all possible directions, colliding in a random manner with one another and with the walls of the vessel. The pressure exerted by a gas is due to the bombardment of its molecules on the walls of the vessel. This is very clear to us. Now the fourth postulate is the collision between the gas molecules are perfectly elastic, that is, there is no loss of energy during these collisions. The fifth postulate is the distance between the gas molecules being very large, there is no effective force of attraction or repulsion between them. As molecules are far apart, they do not have any force of attraction or repulsion within themselves. Now the sixth is the gas molecules move freely in all directions. Their speed and direction change continuously due to collision among them. As a result, their motion becomes zigzag or random. The seventh is the average kinetic energy of the gas molecules is directly proportional to the absolute temperature of the gas. And the eighth is that there is no effect of gravity on the gas molecules. So these are very obvious, and we have understood what they mean, these postulates. Now we'll do the justification for the postulates. Now first postulate, the justification for the first postulate is that the first postulate is in accordance with the general particle nature of the matter. Now second, the justification for the second postulate: when high pressure is applied, the volume of the gases decreases to a very small value because the molecules are very far apart from each other. When we apply gas, then their volume squeeze out. So extreme compressibility of the gases indicate that most of the space in the gases is empty. In fact, the gases can be compressed to a volume which is less than 0.1% of its original volume. This indicates that the volume occupied by the gas molecule is almost negligible. Now the justification of the postulate 3: when a molecule hits the walls of the vessel, it exerts a small force per unit area, that is pressure, on it. The sum of hits of all the molecules in the walls of the vessel gives total pressure of the gas. Now the justification of the postulate 4: suppose the molecules' collisions are not elastic, then the molecule will lose energy at each collision. The kinetic energy will ultimately decrease to zero. The molecules will come to rest and settle at the bottom of the vessel. Since molecules are at rest, these will not collide at the walls of the vessel, thus the gas will show no pressure. But this never happens, hence the postulate is justified. Now for the fifth postulate: gases can be compressed on application of high pressure. It might be due to force of attraction between the molecules, but when pressure is released, these gases will fill the whole space available to them. Hence there is no effective force of attraction or repulsion between molecules. Next is the haphazard motion of gas molecules can be observed in a beam of light falling on the cinema screens. The solid dust particles are hit by gas molecules present in air. The dust particles come in haphazard motion called Brownian motion. For the postulate 7, when a gas is heated, the temperature of the gas increased, and hence the speed and the average kinetic energy of the molecule increases. It means average kinetic energy is directly proportional to absolute temperature. Now comes for the postulate 8: heavier gases do not form the lower layer in a mixture of gases. These form a homogeneous mixture due to diffusion. Thus, there is no effect of gravity in gas molecule. So, I hope that you have understood the things. Thank you very much. Thank you.